Okay, thank you. Hey, welcome to EarthSky. Dave Adalian here, and I am joined today for a talk about climate chaos with Daniel Swain, who is a climate communicator. He is both a meteorologist and a climatologist, and he is active at several very impressive institutions. The Institute of the Environment and Sustainability at UCLA, that's the University of California, Los Angeles. He is a research fellow at the Capacity Center for Climate and Weather Extremes at the National Center for Atmospheric Research, and at the Nature Conservancy. And his work identifies climate related causes for increasingly frequent and severe wildfires, a global phenomenon, and how to mitigate their impact. But not just that, also floods and heat waves and all of the concomitant weather that we get in a warming world. Daniel, thank you for being here today. Really appreciate it.
Thanks
How
for
are you?
having me. You're catching me in a very relevant week, as it
I
were.
am. I am. I am. So, the first thing I wanted to actually ask you about is climate chaos, the title of our presentation today. Is that fair? Is that accurate? Is our climate in chaos, more chaos than it should be? It is a chaotic system.
Yeah, and I think you sort of encapsulated it right there with that last statement that the Earth's atmosphere is something that varies pretty widely, even absent human-caused climate change, which of course is occurring. But even absent
There
that
is.
for a moment, it's something that changes greatly over from day to day, which variations in the weather, year to year variations in sort of the short-term climate, and then much longer-term variations over hundreds and even thousands of years. So there is this high degree of background variability in the Earth's climate. And so we sometimes hear, well, the Earth's climate is always changing. And of course, that's true. But what we do see, at this point in time, is a climate that, over the course of decades, is changing at a pace that is astonishingly fast from a longer-term sort of geological Earth history perspective. So fast, even that we can sort of detect these changes, even notice them qualitatively over the course of individual human lifespan. I can, and I'm not all that old. So
No, you're not.
there's two ways to answer this. I mean, one is that we are seeing more extreme heat waves, more extreme precipitation events, more intense certain types of storms, more severe wildfires. So in a certain sense, yes, we are seeing more extremes. Now, the question is, scientifically, you could ask that question, are we seeing more extremes relative to the historical thresholds that we're used to? And the answer there is yes. Are we
Yes.
seeing more unpredictability of the system, more sort of chaos in the more colloquial sense rather than in the mathematical sense? And there the
Exactly.
answer is a little bit more complicated.
Okay. Well, explain it to us. You connect the dots. You are a science. That's your thing is to connect the dots between climate change, which doesn't just involve warming, and these more extreme events. How do we do that? How do you do that?
Yeah, so fundamentally what's happening with global warming and human-caused climate change, two terms that increasingly are used largely interchangeably. They probably had more of a separation historically. So if you hear me use global warming and climate change interchangeably, that's why. But the climate change we're seeing today, of course, is caused by the accumulation of heat trapping greenhouse gases in the Earth's atmosphere, mainly or almost exclusively at this point due to human activities, industry since the mid 1800s, agriculture, transportation, all of those sorts of things that we hear about all the time. But the reason why that matters, of course, is it doesn't change the amount of energy that the Earth is receiving from the sun, because the sun does what it wants. But what's happening is the energy that is staying within the Earth system that we get from the sun, that fraction of the stuff that stays within the Earth's atmosphere and in the Earth system more broadly, that is what is increasing, because these greenhouse gases are not trapping directly more of the sun's energy, but it's actually trapping more of the radiation, the energy that is being emitted from the Earth itself. So energy comes from the sun, it heats the Earth's surface, then the Earth's surface then wants to radiate some of that energy back to space. In a steady state system where there's no long-term warming or cooling, you're going to have essentially a balance between the energy that's coming into the system and the energy that's leaving. That part, I think, is pretty intuitive. Global warming is happening not because the amount coming in is increasing, but because the amount leaving is decreasing. Fundamentally, that's why we call it a greenhouse. It's kind of like heating up the inside of your car with closed windows on a hot day, or the inside of a traditional greenhouse, which lets the light in and doesn't let the heat escape via convection. And so what we see is that there is this accumulation of energy broadly within the Earth system, and a lot of that goes into the Earth's oceans. So we see warming of the atmosphere, but we also see warming of the ocean. And of course, if you've ever tried to boil a pot of water, which is probably most of us, you can imagine how much energy it takes to increase the temperature of a huge body of water like the ocean by even a fraction of a degree. It's a phenomenal amount of energy. And so if something on the order of 90% of that increasing energy from that imbalance due to the accumulation of greenhouse gases, that's a lot of extra energy that's going not only into the ocean, but if the other 10% essentially or so is what's heating the atmosphere, and we've seen as much warming as we have, yikes, that's a lot of energy going into other places that we haven't even tangibly noticed to the same extent. But it's still there. It's still contributing to what we're seeing, because these warmer oceans, the warmer atmosphere, we see, as you mentioned, it's not just temperature. We see faster rates of potential evaporation. So we see more higher ceiling on how much water vapor can be in the atmosphere. In fact, that increases exponentially for a linear warming. So you increase the temperature of the Earth by a degree centigrade, or about 1.8 degrees Fahrenheit, and you increase the water vapor holding capacity of the atmosphere by 7%. And so all of us would probably be jealous to have a 7% compound interest rate on a savings account in the bank or something. Some of us are burdened with loans with an interest rate comparable to that instead. But either way, you're pretty well aware of just how profound 7% compound growth is. And that's what we see with warming, is that the thermodynamics of the atmosphere, the moisture component of global warming, scales at the 7% rate. It means that both the ceiling on how intense precipitation can become increases by around 7% per degree centigrade, which is, again, fast, and means that each additional increment is larger than the last in absolute terms. But it also increases the evaporative potential of the atmosphere. So both potentially more extreme precipitation on one side of things, but also faster evolving droughts and more severe wildfires, because the atmosphere is more and more able to extract that water from the landscape. And all of that, of course, plays into how storms develop too, because storms are in large part driven by how much moisture is available and the differences in moisture between one region and another. So all of this cascades into experiencing pretty profound changes in our day-to-day weather.
It sure does. It sure does. And even when we're not seeing a lightning complex set of fires like we did in 2020, we're seeing the park fire. You must be getting a little deja vu, because the same conditions seem to be prevailing now that were prevailing then. This one was caused by arson. Apparently somebody pushed a burning car into a ravine, but it's growing to, last I checked, it was at or near 400,000 acres. And it's creating its own weather now. It's sending up all of the moisture in the ground. Is that going to be the new normal? Are we going to just be stuck with this kind of thing? What's the future going to look like for what? I know that we've gained, threefold wildfire incidents in California, specifically in the West, I suppose, in general. Does that translate to the global picture? Tell us about that.
The wildfire and climate change connection is interesting because it brings together a lot of what we've already been discussing, some disparate threads. And just right off the bat, I'll emphasize that one of there are multiple reasons why we're seeing worse wildfires in California and in the Western US, and indeed pretty much in all regions globally except for the tropical grasslands. So that's the one exception. That's partly because we've gotten rid of a lot of those tropical grasslands. But anyway, in
God.
places like California and the American West, and even in places that have quite different climates, like the Arctic, the boreal forest, we're seeing these extreme fires up in Canada right now and up in Siberia, and as well as places like the Mediterranean and southeastern Australia, and coastal Chile, and places that have wildfire-prone environments in South America. Places like this, there is this common thread that we are seeing more severe wildfire activity in these regions. And by more severe, I do mean both larger fires, fast-moving fires, but also literally more intense fires, fires that burn at an actual higher temperature, which means that they have greater effects on the landscape. They have greater potential to evade control and greater potential to essentially develop these sorts of exotic fire behaviors that you sort of mentioned, generating their own weather in the form of, for example, pyrocumulonimbus clouds or fire-generated thunderstorm clouds, essentially, as we have seen on many, many recent fires. But the reasons for this vary somewhat from region to region, and in some places, we've suppressed a lot of the natural fire activity that otherwise would have occurred historically over the past century or so for a variety of reasons. And that means that the ecosystems have developed ecosystems that were quite fire adapted, that needed some amount of fire for their health and for their stability, and to prevent some of the fuel buildup that contributes to some of these catastrophic fires. We got rid of that, and so we're sort of reaping the consequences. And then also we have more people across in all of these regions globally who live in high risk fire zones. So compared to 50 or 100 years ago, there's simply more people per square mile in places that are prone to wildfire. So both of those are part of it. But we're also seeing this increase in extreme wildfires in places where nobody lives, in very remote areas. So that's not a population density problem. And in places where we haven't had those policies to reduce fires relative to what they would have been, 100 or 200 years ago. So there is something else going on here. And it turns out that the overarching theme is climate change. It is the warming of the atmosphere that's happening everywhere, essentially, on Earth that has vegetation, which is where wildfires occur, of course. And the main connection is actually a little bit indirect. It's through the modification of the vegetation. So hotter, drier conditions themselves atmospherically can contribute to more extreme fire behavior. This is true, and this is an additional effect. But in many places, the key influence is that this increase in what we call evaporative demand, or the qualitatively the thirstiness of the atmosphere. I sometimes call it the expanding atmospheric sponge effect, because it kind of gives you this very visual metaphor for an atmosphere that wants to absorb more and more water out of a landscape. So evaporating water faster out of soils, in some cases inducing faster and more aggressive transpiration from plants. Because of this, it means that even places that see a fair bit of precipitation, as is the case in Northern California, can see much faster rates of water loss and drying of the vegetation. And in California, of course, the summer is the dry season. That's not true everywhere on Earth.
No.
But in California, it's quite dry on average between June and August, certainly, and maybe even into September or October in a lot of years. So there's this built-in annual drought. That's just a typical part of the climate in this part of the world. So you always have drier vegetation by the end of summer than you do at the beginning. But what we see in a warming climate is that the peak seasonal dryness is even drier than it used to be and lasts for a longer period into fall in many years, which is a problem in California specifically because we have these what are known as offshore winds, these hot, dry winds that blow from land to sea and are responsible for a lot of California's major wildfire activities. So all this put together means that vegetation, not just in California, but in many of these fire-prone and even some not-so-fire-prone regions globally, is getting drier, if not on average, at least in the extremes. So the driest dries get drier, and that's precisely when you see these huge spikes in wildfire activities. So we see, yes, hotter, drier air in a lot of cases that facilitates fire spread, but more importantly, in a lot of cases, more extremely dry vegetation that supports more intense fire activity, faster spreading fire activity, and more extreme fire behavior, all of which cause problems for both ecosystems and for the humans who live within them.
That is a problem. Yeah. So that sort of change in the hydration of vegetation. Is that what we're seeing up in Canada right now? Because they're having fires in areas, as you say, we don't normally see those kinds of wildfires. Is that what's going on in Canada?
Yeah, I mean, this is essentially the unifying theme, as I mentioned. I mean, this is an effect that is playing out everywhere from the Amazon rainforest, so, tropical rainforest near the equator, to California and the Southwest, the semi-arid environment, very different from the Amazon. And then again, in the boreal forests of Canada and Siberia, a completely different environment, both climatologically and ecologically, than either of those other two places. And yet we're still seeing these effects. And this is primarily because of the rapid drying effect of a hotter atmosphere. Now, just to be clear, it does not mean it's getting hotter and drier well, it's getting hotter all the time pretty much everywhere, but it is not getting drier all the time everywhere. It just needs to be drier than it used to be at least some of the time. And those are the periods where you see these huge episodes of wildfire activity. In the boreal forests of Canada, for example, it is getting wetter on average, but we're still seeing more extreme wildfire activity. And this is sort of why, first of all, why we can't just look at changes in the average values of different quantities to totally infer everything about what's happening. But it also explains specifically in this case why we can see in a place that's getting warmer and maybe even moister on average, why we're still seeing more severe wildfires is because of what's happening in the upper extreme of the hot and dry distribution rather than what's happening on average that's really driving this.
So when we have these events in places like Siberia, that's released, this is becoming a runaway effect. We're releasing methane with these events, and that's increasing the greenhouse effect, and that's increasing the amount of trapped energy. Is that same cycle somehow responsible for the flooding and droughts, things like that? Or are those knock-on effects from things like wildfires and changes in vegetative states and things like that? Vegetation.
There's a lot embedded in here, so I'll approach sort of this piecemeal. The first bit is, these fires emitting significant amounts of greenhouse gases back into the atmosphere, which is in turn acting as a sort of a vicious or self-reinforcing feedback, where you get more fires, you have more carbon emissions, you have more warming, then you have more fires, etc. And to a certain extent, yes, this is true. I would be careful not to call it a runaway effect, because that makes people think about Venus or something. And fortunately, that is not a plausible future for Earth in the next, thousands of years, even on a really pessimistic global warming trajectory. So I hesitate to call it good news, but I suppose it would be worse news if we were headed for a Venus-like atmosphere. So we are not. And Venus does have this runaway effect where this initial warming can beget even larger increments of additional follow-on warming and classic runaway warming effect. So that's not what we see. Still, though, it is still a positive feedback where the more warming there is, the more we see large pulses of carbon into the atmosphere from increasingly extreme wildfires. And that does have an incremental additional warming effect. So while it's not a runaway, it does result in a little bit more warming, which results in a little bit more wildfire, which results in a little bit more warming. So it isn't great. It still isn't a key contributor to global greenhouse gas emissions. Humans still dominate that by an order of magnitude. But it is becoming something that was once thought to be pretty negligible to maybe not being so negligible. It's modest, but it is there and it is increasing. So that is one challenge. The other piece here that you mentioned, sort of, what's the connection to these other sorts of events, the floods, the heat waves,
Right.
things like that. So this expanding atmospheric sponge effect that I mentioned, it does operate like a sponge can. It can both absorb water, and if you wring it out, it will yield more water also. But there has to be water available to do that. So that's why I like to use this analogy, because it works almost unnervingly well in a very literal sense in a warming climate, because there's this notion that it's a basic product of physical chemistry. Essentially, it's known as the Clausius-Clapeyron relation. This 7% per degree centigrade or 3 or 4% per degree Fahrenheit increase in what's known as the saturation vapor pressure of the air over a fluid. So if you heat the air up above a lake or a pan of water in an idealized laboratory setting, the amount of absolute water or whatever fluid that you're doing this over, we'll use water because that's analogous to Earth with our oceans and our lakes and everything else. It increases by that 3 or 4% per degree Fahrenheit or 7% per degree centigrade, just as a function of how physics and chemistry work. This is a pretty fundamental process that's been understood now for a better part of 2 centuries. And this drives so much of what we see on a warming Earth, because not only does it raise the ceiling on how much water can be there, which means that if you're saturated, then it actually raises how much water truly is in the atmosphere. And that's the case when you have, say, an extreme precipitation event. If it's cloudy and precipitating, you have a saturated atmosphere, there's a much higher ceiling on how much water can be there by about 7% per degree centigrade. So if you think of that as the saturated sponge that's completely soaked and you're wringing it out now, with this precipitation event, you can get more extreme precipitation. That's sort of the wet side of the expanding atmospheric sponge, if you will. But on the dry side, we're talking about droughts and wildfires. You can see how if there isn't enough water to evaporate, if there's only a little bit of water that's spilled on your kitchen counter and you have a comically oversized kitchen sponge, well, it's going to absorb all of that water and have a lot of room left to absorb more water. Meaning that essentially, if there isn't an infinite amount of water to evaporate, that increasing ceiling actually means that you're demanding more water from the landscape. You're just extracting it out of soils, out of plants, out of bodies of water. And so in one fell swoop, with this one sort of analogy, this expanding atmospheric sponge, you can explain most of what's going on in terms of why precipitation extremes are increasing, why the most severe droughts in places susceptible to heat waves are increasing, why wildfires are getting worse. And even it turns out that these things, and this gets a little bit more into the weeds, so I won't go too far into it, but it can even explain indirectly things that are secondarily and to a third order related to atmospheric moisture. And that includes things like severe thunderstorms and the jet stream extremes and hurricanes, tropical cyclones. So all of a sudden, you sort of understand how this basic scaling relationship works, and you start to understand a good 70 or 80% of why all of these other extremes are also changing in the way that they are.
It truly is a holistic system where all things are interconnected inseparably. One thing changes and there's a cascading effect throughout the entire system. And you're giving us a real education here, Daniel. So I'd like to thank you for that. And remember, folks, if you want more of this, weatherwest.com is Daniel's home. He's on YouTube. Go watch his videos there. Very educational. And I'd like to thank you for that, the education here. And so would Carla Jean in the Monterey Bay Area, who writes in to say that she's getting a much better understanding here. But you're also scaring us a little bit here. I mean, this is concerning stuff. And you've been doing this a really long time. This is the weather and climate, something you became fascinated with as a young boy. How do you stay positive with all of this change in our home? Our home is changing rapidly, and these are uncertain times. How do you come to grips with that? How do you stay positive?
Yeah, I mean, as you mentioned, I am both a weather scientist and a climate scientist, which means that for me, part of the personal fascination with this comes from just having this genuine interest in the atmosphere. And so being able to operate in this space where we're thinking about the atmosphere doing sort of these new and scary things, for a scientist, it can also be new and exciting things. So there's some intellectual curiosity in there. But the reality is, as a climate scientist, you're always acutely aware of the harm that it's causing, or at least the potential harm. But maybe that framing is sort of important too. The notion that the harm is potential and not inherent to all of these things. And there's an emerging understanding that disasters have a strong human component. It's sort of an extension of the notion that if a tree falls in the forest and no one is there to witness it, it did, of course, really fall. But then the question is if it really mattered. The corollary then is, if there is an extreme wildfire, but it occurs out on the landscape where, or if there's if there's a wildfire out there, is that actually a disaster? And if it doesn't destroy homes, if it doesn't cause significant ecosystem loss, The answer may be no. If there's a flood in the desert, that the arroyos and the washes fill up one day, but it doesn't run into anyone's neighborhood, is that a disaster? I would argue that the answer is no. So I think that but then on the other end of the extreme, we've seen what happens when these sorts of events do affect people, and it can be a genuine, horrifying catastrophe. And so the question is, how do we push these events from being more in the catastrophe, human disaster side of things into being these events that are simply events that are occurring in the world around us? And of course, we can't always prevent all the harm. That's the reality in some cases. But the other reality is that there's a lot of potential harm that can be averted or avoided if we think about these sorts of events and plan for them and adapt to them accordingly. And so I think a lot of, what I try and do is work with folks all the way from the individual level to the federal government and executive branch level to really think about how to incorporate the knowledge that we have about how extreme events, extreme weather events, and extreme sort of weather adjacent events, I'll call them, maybe like wildfires, for example, are changing, and how we can improve our resilience to these sorts of things by active intervention, and not just shrugging our shoulders and saying, well, it's all going to hell. Oh, well, not a lot we can do about it. Because the answer is there is a lot we can do about how the events affect us. It is harder in the long run, of course, to stop the increase in the extremes. And, in a global scale, we need to slow rapidly and then halt the global warming itself. So then there's the question about how do we bring our society so that we stop emitting all of this extra carbon into the atmosphere that has all these negative externalities. That's the big picture solution. But the smaller scale solution, which I think is a little bit more tractable at levels anywhere from sort of an individual to a city or state level, is, in the meantime, how do we make it so that when these events occur, they aren't as destructive as they might be? And I have various optimistic and pessimistic stories about how good or bad a job we're doing at actually accomplishing those goals. But I think my point is that the disaster isn't the inevitable piece. So the extreme event may be something we really can't prevent, but the severe consequences from it, in many cases, are something that is at least partially preventable or mitigatable. And so that's sort of where some of the optimism comes from. And the other piece, is that at a very large scale, the good news and the bad news is that the global warming we're currently experiencing is caused by human activities. It's bad news because it means that we haven't yet stopped doing these things. This year, global CO2 will not only have reached the highest level we've ever seen in human history, but also the largest annual increment that we've seen. So that's actually an acceleration of the rate of CO2 increase. But the good news is that people are now aware of this, and we're trying really hard to bend that curve. We have not done it yet. Don't get me wrong. So we have not yet turned the ship, but we could. If this was some exogenous problem, what if it really were the sun? Wouldn't that be scarier? Because what would we do about that? If this were the sun sending the Earth more energy, I'm not sure what we would be able to, solve the problem. If this was some alien laser beam, that would be pretty bad news. I think both of those would be worse news than the reality that we have now, which is that it's something as simple as combusting all of the hydrocarbons that are beneath the Earth's surface. All we got to do is stop doing that, and we solve the problem. Now, of course, it's not actually that simple, if only it were. But my point is, all the available science suggests that when we do that the warming will slow rapidly and then stop shortly thereafter. So this is not, so when people say that, the warming is baked into the system, that's less a question of geophysical inertia, if you will, than it is geopolitical inertia. And that's something we have control over, and that can change pretty quickly if we so choose. So, the good news is that we can stop global warming. The bad news is we haven't done it yet. And we would need to do a lot more than we're currently doing to do it. So, as you mentioned, as somebody who's constantly embedded in these extremes and these disasters, and frankly, who experiences a number of them, I've been in the middle of, historically destructive wildfires, in the community where I live in recent years. Just this year, it's just been this unceasingly dry and hot period that we've never observed before. I'm talking to you from Boulder, Colorado, along the Front Range of the Rockies. And it's literally never been this dry and hot in recorded history in this part of the country. So that's making folks nervous. So constantly being embedded in this, talking with journalists, talking with people personally experiencing these escalating meteorological extremes, these historically unprecedented extremes. I mean, again, I'm 35 and I've experienced a whole lot of historically unprecedented climate events that in a stable climate, you would have to be extraordinarily unlucky to experience that many. Now, I don't think I'm particularly unlucky. I think it's just an indicator of how profoundly our climate has shifted over just 30 or 40 years.
So the good news is that it could be ameliorated, if not cured. There are things we can do about the extremes. They don't have to be disasters, but also we can address the overarching problem of the giant sponge by shrinking the sponge, by stopping burning fossil fuels and reducing humanity's carbon footprint. So what is the biggest factor right now adding to our carbon output? It's not people, it's not individuals, is it? It's corporations and institutions, or is it? What's your take on that? And how might we address that, do you think? Because you just framed this as a political problem, and it certainly is.
Yeah, I mean, I think that this is the challenge, is that it is such a big problem precisely because everything that we do in modern society, essentially, either directly or indirectly, emits heat trapping greenhouse gases into the atmosphere. That's true. Even I'm very painfully cognizant, aware of that fact, and I am 100% certain that in my own life, I cause a lot of carbon to be added to the atmosphere in the way things currently exist. Most of us in the modern world do, some more than others. There is definitely an equity issue here, where some of the folks who are most affected by climate change have historically contributed the least amount of greenhouse gases to that warming. But the fact remains that living in the modern world means right now emitting a lot of carbon into the atmosphere, which harms everybody collectively. And this is because just about everything we do, so industry, of course, emits carbon. Transportation, in most cases, the way it's currently set up, emits carbon. But even things like large-scale agriculture is a huge source of carbon for the atmosphere. So the food we eat, the homes we live in, and everything we use to get around and go to work and do our daily lives, all things that we can't stop doing, emit huge amounts of carbon. So then folks say, well, then how the heck can we solve this problem if everything contributes to the problem? And the answer is that no one's saying we should stop eating or working or living indoors or traveling even. The argument is that all of those things can be done either with vastly reduced carbon footprints or even essentially net zero carbon if we do them differently. But the problem is that means retooling everything. Essentially, it's going to involve a transformational shift in the way we engage in all of these activities, the way we get around, the way we grow our food, the way we do industrial activities. All of these things have to change in their own ways. And all of them essentially are things that are beyond what any individual can achieve. I don't know, maybe there are some billionaires out there who essentially have so much power in today's world that they can exert meaningful influence. But at a typical individual level, we are constrained by the choices that are available to us to a large extent. And even people who try and make really good low carbon choices, frankly, still end up having a carbon footprint that is unsustainable. And so that's not an inherent reality. It's just the way the systems are set up right now. So large scale change in all of these sectors is what we need to make it trivially easy to make good decisions, so that the easy, lazy decision, essentially, that a lot of us like to make about most daily activities. I mean, who wants to overthink every step you take every day? We need the systems to exist in a way where the default option is one that doesn't harm the climate. And I think we can get there, but we're not there yet, and there is a long way to go. And this is going to require buy-in from everyone. And this is why it is a political problem ultimately, is that individuals are actually a lot more inclined to address the problem than the political systems that ostensibly represent them in most countries. And this is, of course, a whole different question veering into the, electoral politics and everything like that. But I think the reality is that, and this is true this year, this is a very consequential election year in the United States and has been in some other countries as well, where climate has actually played a role in some of the decisions that people have ultimately made in other countries so far this year. I know there's a lot of distractions this year, but this is a huge climate election on top of everything else. And so I know it may sound weird for a climate scientist to say global warming is largely a political problem, but I think it is, because physically we understand what we need to do to solve it at a macro scale. It's not easy to implement it, but it could be implemented, and it requires large scale change. And so I think the most important things that individuals can do to bring that about is to demand that large scale change. It's not so much that changing out your light bulbs and eating a lower carbon diet isn't constructive, but the main reason it's helpful is not because of the actual carbon that you're not personally putting into the atmosphere through those actions. It's in the signal it's sending to corporations, to industries, to politicians about what you want and about what you think is important. So that's sort of my perspective. It's really important to be active and just to talk about climate change with other people. Surveys over and over again show that the average American doesn't hear about climate change in the typical month once. I know that can be hard to believe for people who are really plugged into the news and weather and climate, but that is the reality. So even just having casual conversations about it with friends and family and acquaintances at the coffee shop, or your Lyft or Uber driver, something that I do when I'm traveling, and always results in interesting conversations in one direction or the other. But I think that's important, as well as voting when you're able to do so and with climate in mind, because there are huge differences between the proposed policies between candidates. This has always been true, but 2024 is, as much on top of everything else, it's also the largest climate change related election of our lifetimes.
Well, you said it. You said it very succinctly. Vote with climate in mind, but vote with your dollars as well as at the ballot box, I would think. So support those companies who are demonstrating that this is a problem, but it can be solved. And the way to do that is to act on a larger scale. So everybody, yeah, definitely, you know, buy an electric car, you know, walk to work, but also put pressure on people not to institutionalize the the burning of carbon, the release of carbon. Um, so I think that we have pretty much covered everything and done it really well. Do you have a parting message for us? You know, so talk, besides, you know, talk a lot about climate change, mention it with friends, but stay positive. How do you do that specifically?
Well, to be quite honest, I'm not sure that I always stay positive. I mean, I am somebody who's constantly enmeshed in when things go wrong, in the most extreme events that tend to be the ones that cause the most harm. It's both what I study scientifically. It's also what I talk about the most with people, because, journalists usually aren't calling me, for example, when there's a day that's close to the average temperature without any remarkable precipitation. I mean, what's the news story there? So preferentially, and understandably, I don't think it's a bad thing to talk about big bad things when they happen. It's also important to remember that's not what's going on all of the time. We still have days and weeks and months and years that are not so extreme. California just experienced that, for example, 2 years in a row without, really severe wildfire seasons. 2022 and 2023 were quite mild, harkening back to much earlier in the 20th century. One thing that I think was maybe a bit of a missed opportunity in that window is taking advantage of these relatively favorable weather conditions in some cases to do things like prescribed burning, which can reduce the risk of subsequent catastrophic fires, can help make ecosystems more resilient to the changes we know are happening, but you can't do them all the time safely. You kind of have to wait for these windows that are appropriate to have fire that's robust enough to do its job and actually clear out some of that vegetation, but not so intense that you end up just igniting an accidentally an uncontrolled wildfire that causes problems. So it's this Goldilocks setting, for example. And there was, of course, some prescribed burning. There's more of it than there used to be, which is good. There's been progress, but we could have done a lot more over the past couple of years. And now, of course, as we've seeing much more extreme wildfire activity again in California, as we experience record heat and things really dry out again, we're sort of entering another cycle where that's going to be harder to do. So I think one lesson in all of this is to realize that it isn't, even though it feels like it may just be this constant onslaught of extremes, in any given place, you still get pretty significant breaks. And my hope is that, as some of these extremes continue to escalate, which they are, and that is concerning, we learn better to take advantage of the windows that are available to us. This is one regionally specific example, with prescribed burning in California, but this is true in other regions. Thinking about resilience in urban areas to extreme heat waves, or years where there's not much hurricane activity, thinking about how we can strengthen our coastal resilience in a climate with higher sea levels and more intense hurricanes in places that experience them. So it's just an example of how, we really need to be proactive about these sorts of climate adaptations. And although it can be exhausting when we have these periods of sustainedly unprecedented events, and we have had long strings of them recently, your mileage varies locally. And so you do have opportunities to sort of get in there and do that work.
Things like building sponge cities like Los Angeles and
Exactly.
all over China and things like that. We are running up on the top of the hour, Daniel, and I know you have a busy media day ahead of you. So I want to thank you for the education, for the uplift, because there are things that we can do about this. This is not the end. This is not our doom, but this is something we definitely better address. But next week, and one more thing, please go and visit weatherwest.com. Subscribe if you have not to Daniel's YouTube channel. It's great. He really gets in there and gives you the lowdown on what is happening in our climate and the weather. And next week, we are going to be talking about the Perseids meteor shower, which is coming up in August. It's meteor time. And Debbie will be here to host, along with Robert Lunsford, who is a meteor expert, meteor expert. And so we hope you'll join us for that. Daniel, thank you one more time. Really appreciate you being here. Folks, like and subscribe. Go visit Daniel's sites, stay in touch, and we'll see you next time. Thank you very much.
Thank you.
Thanks, Daniel.